When substances form solids, they tend to pack together to form ordered arrays of atoms, ions, or molecules. Let's see how this order arises and what different kinds of arrangements are possible. Many a times, oranges or apples stacked nicely on a vendor's cart catch your attention. It is a practical application of close packing. A honeycomb is an excellent example of close packing found in nature. A close packing is thus defined as a way of arranging equidimensional objects in space, such that the available space is filled very efficiently. Solids are three-dimensional objects, and we will develop their structure in 3 steps. To understand how the constituent particles are packed, let us assume that these particles are hard spheres of identical size. First, let's look at close packing in 1 dimension. You can see that there is only one way of arranging the spheres in a one-dimensional close-packed structure, that is, by arranging them in a row touching each other. In this arrangement, each sphere touches 2 neighboring spheres. In general, the number of nearest neighbors of a particle is defined as its coordination number. Therefore, the coordination number of a particle or sphere in one-dimensional close packing is 2. Let's now look at close packing in 2 dimensions. When a number of rows are stacked up, a 2-dimensional crystal plane is generated. Obviously, there are 2 ways of stacking the rows. One way is for the rows to lie one above the other, with one sphere exactly above another. You can see that the spheres are aligned horizontally as well as vertically. If the arrangement of the spheres in the first row is said to be of A type, then the arrangement of the spheres in the successive rows is also of A type. The packing thus obtained is called AAA type packing. You can also see that each sphere is in contact with 4 other spheres, 2 on either side, 1 above and 1 below. Hence, the coordination number becomes 4. Also, if you join the centers of these 4 spheres, you will get a square. Therefore, this type of close packing is also referred to as square close packing. The other way is for the spheres of the second row to be seated on the first row in a staggered manner. That is, in the depressions of the first layer. The spheres of the third layer are placed in the depressions of the second layer, and so on. Evidently, the spheres in the third row are vertically aligned with the spheres in the first row. This pattern is followed throughout. If the arrangement of the spheres in the first layer is of A type, then the arrangement of the spheres in the second layer is of B type, and the arrangement of the spheres in the third layer is again of A type, and so on. The packing thus obtained is called ABAB type packing. You can also see that each sphere is in contact with 6 other spheres, 2 on either side, 2 in the layer below, and 2 more in the layer above. Hence, the coordination number of a sphere becomes 6. Also, if you join the centers of these 6 spheres, you get a hexagonal pattern. Therefore, this type of close packing is also referred to as hexagonal close packing. If you compare the two arrangements, you can see that in hexagonal close packing, the constituent spheres occupy the space more efficiently. Therefore, constituent particles will arrange themselves in hexagonal close packing in a plane or 2 dimensions. Some spaces are left vacant after the close packing of the spheres. These vacant spaces are called voids or interstitial sites. In the figure, the empty spaces are seen as curved triangular spaces. These spaces left between the spheres can be divided into 2 kinds, B and C. The spaces marked B are the ones in which the apex of the triangular spaces is pointing downwards, while the spaces marked C are the ones in which the apex of the triangular spaces is pointing upwards. As real crystals are all 3-dimensional in nature, we will use this 2-dimensional hexagonal close packing to build 3-dimensional structures later on in this course.